Okay, so hopefully you didn't watch all of that 10-minute video and you just caught the last exciting minute there. But I thought the exchange was kind of fun and kind of helps reinforce these ideas of remainders and mods and congruences. So let's figure out and outline this process to complete this game and impress all your friends. So with my mom's number, I knew that it was congruent to 5 mod 11 and it was congruent to 10 mod 13. And so what I did, it's basically works with substitution and a bunch of kind of cool, interesting things going on. So if you want the Chinese remainder theorem, I think it's proved. I think it's proved in these notes here, and also definitely in your text. But so it might be worth it to kind of help this process make more sense. And so if you wanted to go through, well, I guess it doesn't prove it in the notes, but it definitely proves it. Oh no, yeah, it does. It does. So basically what we call this the Chinese remainder theorem is that the method that we follow is constructed in the proof of the Chinese remainder theorem. And if you read the proof, it's just gonna be crazy, okay? So, but just know that the proof is there and that's why this method works. So if you want to see why it works, look through that proof. But I think it's just kind of a fun little process to go through and complete. So I'm going to try to outline the steps I took to find this congruence, or to solve this congruence, because this is a system, right? I want to solve these equations simultaneously and find an x that satisfies both of them. So the first thing that you want to do when you're trying to complete the process outlined in the Chinese remainder theorem proof is put all your information into a table to organize it. I think it'll help make things better. And so the notation that you're going to see is A sub k. And so when you're given a system of congruences, that label is for these particular integers that our variable that we're interested in is congruent to. So, or maybe we've got our congruences, okay? So we're interested in this particular integer. And so what I'm going to do, I'm going to have 2 rows in my table for my 2 congruences. So let me just, maybe I'll label them here. So this represents equation, or congruence 1. I'm going to put all the information in there, okay? So I'm going to put 5 here for that first equation. For the second equation, I'm going to write 10. And then the next thing I have, m sub k, okay? And all this is just the particular mod with the congruence that we're talking about. And it's really important here to note that this system has a solution only if all of these mods are pairwise relatively prime, which means it's not that interesting here with just 2 congruences. It just means that, the GCD of 11 and 13 is 1, so they're relatively prime. They don't have any common factors. But if we had 3 congruences, here, let me look at an example here, actually. So like in this problem, I've got x is congruent to 1 mod 4. So I'm dealing with 4, 5, and 7. So what I'd have to do is take all possible pairs here and show that they're relatively prime, show that they have no common factors. 4. And notice, like, the order that I input these doesn't matter. So hint, hint, we're working with a combination versus a permutation, okay? So kind of a little nod to the upcoming counting stuff. And so we get 3 possible combinations here of 2. And let's see, 4, 7, 5, and 7. So since all these all these pairs are relatively prime, I know that the Chinese remainder theorem states that this system of congruences has a solution. So if you look at the statement, which probably looks crazy, the only, well, there's a couple of conditions. These mods have to be relatively prime. Also, these have to be integers. Also, notice there's no coefficients here on the x, okay? But it's possible you could get rid of those coefficients by solving for x, you know, not get rid of, but manipulate that congruence, okay? So keep that in mind. So the way that they've set up this game that I found online is they have two relatively prime mods that we're dealing with, 13 and 11. So we've satisfied that condition. So that's what that MK represents in our table. So I've got 11 and I've got 13. Okay. Now, we want to try to take these two congruences, which are written in different mods, and try to write them all under the same mod. And this is kind of confusing because we were kind of harping before about being careful combining mods. But remember, if that mod divides into another, we have some tools in our kit to deal with that. So basically what we're going to do, instead of trying to deal with mod 11 or mod 13, we're going to combine those two mods, and this M is just the product of all our mods. So it's going to be 143. And so notice this game works because we hit all possible numbers from 0 to 100 here. So this product being greater than 100 is important. So if you want to play with the mods, you can. You could do this with like 3 steps and have them divide by like 5, 7, and 9, because that will give you more than 100. Or you could do like, I don't know, 17 and 21. That'd be, yeah. So there's some options there for you. But, so let's see. So the next column that we're going to do is we're going to take M and divide it by the corresponding mod in our particular equation. So I'm going to take 143, divide it by 11. I'll get 13 here. I've got 143, and I'm going to divide it by 13 to get 11. Okay. Now this column is the one, this next one is going to be the one that's going to take you some time to wrap your head around and believe and calculate, okay? So this one, you're going to find the inverse of M divided by MK mod MK, okay? So I'm looking for the inverse of 13 mod 11 and the inverse of 11 mod 13. If you feel comfortable with the extended Euclidean algorithm, you go ahead and fast forward these next few minutes. What I'm going to do is I'm going to figure this out by hand using the extended Euclidean algorithm. But notice you can just plug it into your spreadsheet and you get the solution there within that spreadsheet. But I'm just going to show you by hand because it's not too bad. So the first thing I'm trying to do, I'm trying to find the inverse. Now I'm going to write this as 13 to the negative 1 mod 11, okay? And what I mean by negative 1 is not negative 1 in the traditional sense, but what I mean is inverse, okay? So that's why I'm not a big fan of that notation, but it will come up. It does come up later on in math, so I think it's okay to kind of transition to that representation of inverse. And probably in college algebra you noticed it too, so that's not too crazy. So what I'm going to do to find an inverse, right, what I'm looking for when I say that is, remember, I'm looking for a number that I multiply by 13 that will be congruent to 1 mod 11. So I'm looking to find this A. And remember, the extended Euclidean algorithm gives us that number. So as long as the numbers are relatively prime, okay? If they're not, then yeah, there's a whole other story, okay? So what we're going to do is first we're going to use the Euclidean algorithm to find the GCD of 13 and 11, okay? So if I find the GCD of 13 and 11, I know 11 goes into 13 one time with a remainder of 2. And then my divisor becomes my dividend, and my remainder becomes my divisor. And now my divisor becomes my dividend, my remainder becomes my divisor, And I get a 0 remainder, so I want to focus on the first two. I know my GCD is 1. They're relatively prime, so that's good. We're going to be able to complete this process to find the inverse. So what I'm going to do first with the extended Euclidean algorithm is solve for my remainders. Solve for remainders. Okay. So I have 2 is equal to 13 minus 11. And I have 1 is equal to 11 minus 2 times 5. Okay. All right, so ultimately what I want to end up to figure out the inverse, I want to figure out how to write 1 as a combination of 13 and 11, a linear combination of 13 and 11. Because these values are going to give me those inverses. Okay. And once we get those values, we'll talk a little bit more about why that information is there in that linear combination. But okay, so I like the equals 1 part. I'm gonna stick with this one and start here. Okay, so I'm going to start with the equation 1 is equal to 11 minus 2 times 5 because I want to end up with something equal to 1, so I like that. Now I've used this equation, so I need to use this one. And so what I can do, notice how 2 appears here. That's always going to happen because that remainder kind of keeps following you along, right? So if you substitute in, there's going to be a place for it to be substituted. So I'm going to take, instead of 2, I'm going to write 13 minus 11, okay? You have to be really careful with parentheses here. This is negating all of this, and it's all being multiplied by 5, okay? So let me just distribute that 5 so I don't have to worry about it. Now, it's weird because we don't want to actually complete this arithmetic. We're thinking about 11s and 13s as variables. So let me take you here and say, let's say m is equal to 11 and n is equal to 13, okay? I just want to show you another way to think about this to make the simplification a little bit easier. N minus m times 5. So we've got 1 is equal to m. I'm going to distribute the 5 because it's on the right and I just wanted to make sure to take care of it. Minus, sorry about that, minus. Okay. And so I've got this subtraction. I'm subtracting this and that guy. So I will have opposite signs for each of them. So instead of positive here, I'm going to have negative. Instead of negative here, if I subtract a negative value, it'll be a positive value. Okay. Now I've got like terms here. I've got 1m, and I add 5 more, so I've got 6m minus 6n, or 5n. Okay, so now let me go back to these numbers, and we're going to get the same exact thing here, because remember, m was 11, n was 13. So I'm going to distribute that negative 5 times 13, and I'm just not touching the 11 and the 13s. I'm not doing any multiplication because I like those. 11, so this is 111, 5 more is 6. And we don't want that negative there. I want it to be a plus sign. So what I'm going to do is write plus a negative 5 times 13. Now, let's look for this. Let's look at this equation mod 11. Okay. So what I'm going to do is take everything mod 11. 1 mod 11 is 1. 6 times 11 mod 11 is 0 because it's a multiple of 11. Negative 5 times 13, I'm just going to leave as is. I mean, I could put 2 here, but I don't want to because I'm interested in that 13. I want to end up with something like it. So if I combine all these, all this information, so this tells me 1 mod 11 is equal to 0. Right, plus negative 5. Well, I think I need a congruence here. I'm going to write, because I'm going to now write it under the mod 11 word. 1 is congruent to 6 times 11 plus negative 5 times 13 mod 11. Because if it's true here, we can think about here. So this is 0, so I can replace that and just end up with negative 5 times 13. Okay. Now, so I'm saying that the inverse is negative 5. Okay. And if you notice, if you take 13 times negative 5, you get negative 65, negative 65. So if I think about mod 11, negative 65 is equal to 11 times negative 6 plus 1, right? Plus 1. Yeah. So it's congruent to 1. So that's good. That's what we wanted. So this tells me that the inverse of 13 mod 11 is negative 5. So I'm going to put that here. Okay. Now what's nice is that we actually already found the inverse of 11 mod 13. If we look at that linear combination I got, it's going to be 6. And that's because if I look at this equation mod 13, this piece goes to 0, and I'm left with 1 is congruent to 6 times 11 mod 13. Okay? So this tells me that the inverse of 11 mod 13 is 6. And so just to double check, 6 times 11 is 66. If I think about multiples of 13, let's see, 13 times 5 is 65, right? So plus 1, we get that congruence equal to 1, so that means it's an inverse under that mod. So that's where we're going to get our 6 here. All right, now we're going to combine our information, okay? So now we've done all the hard calculations, and now all that's left is multiplication and addition. And then, you know, reducing mod 143, okay? So let me just kind of get rid of some of this mess here. All right, so we're going to take the product, and I built all this stuff into an Excel spreadsheet to help me calculate all this stuff, and it makes it easier. I'm sure you could do that too. I didn't get those to automatically update. I got lazy there, but so that might help you kind of check your work here. But the next thing we're going to do is take our integers, our a sub k's, times m divided by mk times the inverse that we just found. Okay, so we're going to take 5 times 13 times negative 5. Okay, 5 times 13 times negative 5. And I'm going to take 10 times 11 times 6. 10 times 11 times 6. And then I'm going to add those values up. And take the sum of those. And actually, this will be pretty much our solution. I'm just going to take it one more step. So let's see, I've got negative 25 times 13 plus 660 would be 325, which means yeah. So if we add those up, we get 335. So now I just want to take a moment and think about this 335 to end up with a number that's under mod 143. I'm going to go ahead and reduce 335 mod 143 so that I can get a better idea and understanding of my solution. And it would be unique in that mod. So if I take 335 mod 143, this is going to be 335 is equal to 143 times 3. Does it go in there 3 times? I don't think so. 9, no, So we go 2 times. 6, 8, 286. 335 minus 286. There we go. 9. 3, 13 is 59? 59? 50? It's 12. Oh, no. 49. Good. 49. I'm not very good at arithmetic. 143 times 2 plus 49. So this tells me that x is congruent to 49, mod 143. And so that's how I knew it was 49. But I had my little spreadsheet up, so I did it pretty quick. But so let's just verify that this satisfies this system of congruences, okay? So the way that we demonstrate that our solution satisfies the given congruence, or congruence is, right, is we will just plug in that value. We'll plug in the 49 into each of these congruences and for x, and then we'll make sure that those congruences are satisfied. So, I'll write this in a little bit goofy. So let's figure out what 49 is mod 11. So 49 mod 11, I know the closest multiple of 11 to 49 is 44, and I add 5 more. So yeah, I get, since this is x, I get that x is congruent to 5 mod 11. So our proposed x is 49. We just want to check and verify here. All right, now let's talk about mod 13. 49 mod 13. So 13 times 3 is 39. And then we have 10 left over. So yeah, 49 mod 13 is 10. So x, or 49, is congruent to 10 mod 13. Okay, so when you're reporting your final answer, you can just say x is congruent to 49, so this reduced version, mod 143. Now careful, that mod is important, otherwise it gets, we get in trouble. So notice we have an infinite number of solutions to this congruence. If we take 49 and add any multiple of 143, we will get a possible solution. Okay? So hopefully that gives you a little setup. If you look on D2L, there is a couple more resources, a couple more lectures that outline this process. And there's also a example of a solution that I've posted too. So check that out as well, and then let me know how you were doing, and I will talk to you guys soon.